Okay, so 644 nanometer light. So our wavelength is 644 times 10 to the minus 9th meters. Falls on a slit that is that many millimeters wide. So we got to be careful, right? So D is 0.056. Now a millimeter is 10 to the minus third. So I'm just going to go times 10 to the minus third meters, right? Now I know I should say 5.6 times 10 to the minus fifth, but I'm not going to. I'm too lazy. Okay, so let's see. What is the full angular width of the central diffraction peak? Okay, well, it's going to be twice this half width, right? Okay, so let's answer A. Okay, sine of theta is just going to be lambda over d, right? Then this is the half angle, right? I'm going to do half of it, right? So half of the angle is the inverse sine of lambda over d, right? And then twice that, 2 times theta, will be the full angular width, right? Because I'm figuring out this distance here, right? And then we need to figure out this whole thing, right? Euler width, I can do this. Okay, so let's go inverse sine. Sorry, that's the inverse sine. Let's go second sine of the lambda, which is 644, e minus 9 divided by 0.056, e minus 3. And I'm getting the half width is 0.6589. So now I'm just going to, and this is, I'm in degrees. Yes, I am in degrees. Okay, so that's degrees. I'm going to multiply by 2. So times 2 is 1.317. Full angular width is 1.317 degrees. Not very big. All right, so let's see. What is the width? What is its width on a screen that is 4.5 meters away? I think we can do this, right? So B, so here it is. I'm going to go whoop, and then here's this width. It's so hard to draw. You try to draw with a stylus. Okay, so this is 4.5. This is, I'll call that X, right? So X is going to be, I'll use this half width and then double it. So X is going to equal 4.5 times the tangent of 0.6589 degrees. All right. And then I have to double that, right? Because I need to use a right triangle for the inverse or for tangent. Okay, so I can do this. 4.5 tangent of that angle is X is 0.05175, and then if I multiply it by 2, I'll get the full width of it, right? Because I'm going from, I just figured out this distance, but I need to do 2 of it, right? I need to go from this side to this side. So multiply by 2, and I get that the width is equal to 0.103506 meters, which is about 10.4 centimeters. All right. All right, I think I've done all I can do without erasing the screen. Let's do C. I'll erase the screen and do C. What distance separates the central maximum from the third minimum on the screen 4.5 meters away? So that's the distance here. Let's do this. So C, let's do C. What distance separates this from this to the, what is it, the third minimum? 1, 2, 3 is this guy. Right, so that angle, this angle is going to be inverse sine of 3 lambda over d, right? Okay, so that's going to be sine minus 1 of 3 times, 644 times 10 to the minus 9th, right, divided by 0.0560 times 10 to the minus 3rd, because this is millimeters, right? This is nanometers. All right, sorry about my handwriting. All right, inverse sine of 3 times 644 divided by 0.056 e minus 3. And that is, wow, it's a big angle. That's a whopping 1.977 degrees, right? And then I can figure out the distance. So here it is. The screen is 4.50 meters away. It's going to be some distance here. Right? And then if you can imagine that I could draw, oh, that was a good straight line. Look at that. And that angle is 1.977. All right. Degrees. So I can say that x is 4.5 tangent of 1.977. All right. That's 4.5. 4.5 tangent of that angle that I just got. Baby. And I'm getting that distance is 0.1553 meters, or 15.5 meters. There we go, baby. All right.